So let's take a look now at the AP Open Response number 3 from 2005 off Form A. This is one of my all-time favorite questions on linear regression because it has all of the key concepts about, looking at a scatter plot, looking at a residual plot, reading a table that has, all the different types of standard deviations that we may encounter, and it just packs everything in there. It's a really, really, really nice question. So again, make sure you try this on your own for about 12 to 15 minutes before watching the video, and then kind of compare. So let me kind of run through the question before we look at my solution. So we've got a table here that indicates the number of rail cars and then the fuel consumption in units per mile that this train is going to need for the Great Plains Railroad. And this is a random sample of 10 trains. Great, so I've got the table there. And then they've gone ahead and already made the scatter plot where we've got the explanatory variable being the number of rail cars, the response variable being the fuel consumption in units per mile. And we can see just by looking at the scatter plot, I'm thinking about key ideas that the question is probably going to address. So the three key features when I'm looking at a scatter plot, I'm thinking strength, and I'm thinking direction, and I'm thinking shape. And I want to describe all of those things in the context of the problem. So when I'm looking at this, I'm thinking as the number of rail cars increases, the fuel consumption in units per mile also increases. It looks like this is a strong, linear, positive association. So again, notice I'm getting that strong as the strength. Direction, it's positive association. Shape looks fairly linear. And I'm getting all that in the context of the problem, saying that, as the number of rail cars goes up, and the fuel consumption is going up as well. So I'm thinking the question is going to address those ideas. And then we've gone ahead and made a residual plot. Now you'll notice this is a little bit different than residual plots that maybe we've seen in class, in the sense that usually on the x-axis down here, we'll plot the explanatory variable, say the number of rail cars, or maybe the response variable, say the fuel consumption, and then on the y-axis here, we'll plot the residual. So they've gone ahead and plotted some sort of a fitted value. I'm not really sure what that is. I mean, it looks like maybe that could be the fuel consumption. I'm not really sure. But that's kind of not important for this problem. The important thing here is that when you're looking at a residual plot, how can you determine if a particular model is a good fit? Well, here, we're looking at the residuals from a linear regression. And the residuals look randomly scattered, and they don't look to be too far away from the x-axis here. And that's what we want to see if the model is a good fit, is an appropriate model. So if you see a pattern, a curved pattern, any sort of pattern in the residual plot, then that means that whatever model you're using to create that residual plot, that's not an appropriate model. So both the residual plot and the scatter plot are kind of confirming that we've got a strong positive association, linear relationship here. So now let's go on to the next page and look at what we've been given in terms of data. So now we've got this great chart which has all the key information here. Notice the regression equation is given to us right here. Fuel consumption equals 10.7 plus 2.15 rail cars. I mean, I might write that as y hat equals 10.7 plus 2.15x, where x is the number of rail cars and y hat is the predicted fuel consumption in units per mile for a given number of rail cars. So I've got that regression equation right there, and now I've got all this great stuff on the table. So I've got the r squared value is 0.967. I could square root that and find the r value. And I know the R value is going to be positive because that slope on the scatter plot looked like it was positive. So R squared, remember that's the coefficient of determination. Remember that means that 96.7% of the variation in rail cars is explained by this model of fuel consumption versus rail cars. R squared adjusted right here, I don't really know what that is. I mean, I looked it up once, but I can't really remember, and it usually doesn't come up in the problem. So I'm going to put next to it. I don't think I need that there. That S down there, that's the standard deviation of the residuals. And then looking to the table, the coefficient of the constant coefficient in my equation, that's the y-intercept. Constant coefficient, that's the y-intercept, 10.667, and I can see that because, boom, that's the y-intercept in the equation. The coefficient on rail cars, the coefficient on the explanatory variable, that's the slope in the regression, 2.1495, that's the slope. They just rounded it here to 2.15. And then the standard deviations also match up there. The 5.157, that's the standard deviation for the y-intercept. And the standard deviation on the rail cars, that's the standard deviation on the slopes of the regression lines. And then I've got the t-values, my t-score, and then the p-value being the tail probability value that pairs with that particular t-score. Now, I'm not going to talk about that in detail in this video because this particular question does not address looking at a t-test on the slope of the regression line. So if you're unfamiliar with what those are, we'll get to that into some later videos. And now let's check out the answers here. Great. So part A asked about this relationship between the number of rail cars and the fuel consumption. So notice I'm answering that in context, pretty much exactly what I said when I looked at that scatter plot. As the number of rail cars increases, so does the fuel consumption. Scatter plot shows a strong linear positive association. And then I also threw in the piece there about the residual plot. The residual plot shows random scatter, which means that the linear model for fuel consumption versus rail cars is appropriate. Now, you were only asked, you were not asked to defend whether or not you think there's a linear relationship here in multiple ways. I threw in both because I thought that would make my answer kind of holistic and incomplete, but I bet if you had either of them just by themselves, it would be okay. But I feel, why not throw in both there? That's not too long of an answer, and that's a great way to answer this. Also notice that the first thing I wrote down was the answer to the question, which is yes, and then I went on to give evidence to support that in the context of the problem. For part B, it asks for a point estimate. That's just a very fancy way of saying just give a numerical, a single number, an estimate here. So if I increase my rail cars by 1, how much money is that going to cost me? Well, think about the slope. The slope is 2.15, and the units on that would be, that's units of fuel per mile per rail car. So what that is saying is that's saying every time you increase the rail cars by 1, you're predicting, or the model predicts, that you'll need 2.15 more units of fuel per mile for the train. So that means if I get one more rail car, the model is predicting I'll need 2.15 more units of fuel, and it says that the fuel costs $25 per unit. So if I multiply that $25 per unit by the 2.15 additional units that I'm expecting to need, that's going to cost about $53.75. So notice I'm just kind of writing a sentence there. I'm showing my work, which in this case is just multiplying 25 by 2.15 and kind of giving an explanation around it. But that's a pretty straightforward part to the question. Part C I actually answered when I was talking about all of the table and just going through generally what the question was about. So part C just says, interpret R squared in the context of the question. So R squared was 96.7%, or 0.967, so that means that's the percentage of the variation in the response that's explained by the linear model. But I want to say that in context. So it's the percentage of the variation in fuel consumption that's explained by the linear model of fuel consumption versus rail cars. So I'm explaining that in the context of the problem. And then lastly, we're asked if it's appropriate to make a prediction for the amount of units of fuel that we would need per mile if there was 65 rail cars. Now, we've got that linear model. I mean, we could just plug in 65 into X and grab a number for Y hat, for the predicted fuel consumption per mile. So, I mean, I could do the math there. It would take about 2 seconds. I'd just grab my calculator. But that wouldn't be appropriate here because we only collected data on fuel consumption from trains that had between 20 and 50 rail cars. So if we have less rail cars than 20 or more rail cars than 50, maybe the model changes. Maybe it's no longer linear. Maybe it starts to, you need fuel at a much more demanding rate once you go beyond 50 rail cars. We don't know because we didn't collect the data on that. So making a prediction for 65 rail cars for how much fuel you would need per mile, that'd be an extrapolation, not appropriate. That's what they're going for there. So hopefully you had a lot of luck with that problem.